Today we're looking at some more Calculus 2 practice problems focusing on power series. So power series are the same thing as our normal series we've been dealing with, except now there's a variable x to the n term in there. So when you map out the first three terms, they'll be the same, the sequence evaluated at 0, 1, and 2 summed up, except now we have an x in there and an x squared and an x cubed, and it'll keep repeating. You can also center these at some x value c, and that'll show up just like this, x minus c to the n. So there's only three possibilities for these series. They converge only at x equals 0, they converge for all real numbers, or there's some interval of convergence where it will converge if x or values of x are within that interval, and if they're outside that interval, the series will diverge. So we're going to be using the ratio test a lot, and I believe that was 2 videos ago. The ratio test is very important for this section. You could do it with other tests, but the ratio test would be the most efficient. Remember, for the ratio test, for some series a sub n going from 1 to infinity, you take the limit. Everywhere you see an n, you plug in an n plus 1. Divide that by your normal sequence. Take the limit as n approaches infinity. If that's less than 1, the series will converge. If it's greater than 1, the series will diverge. And if that limit's equal to 1, the test is inconclusive. It's often not equal to 1 because this would mean a series, if you're dividing it under the next term, chances are that it's not going to be the same value, so it's really not going to be 1 very often. So we can quickly see if a series is equal to or less than or greater than 1. For example, find the interval of convergence of this series. So you may recognize that this is what we call, when we have a and then some r to the n power, we call this a geometric series. This will converge if the absolute value of r is less than 1. So you can see r in this case is some x minus b. So to recap what we're going to be doing, we want to find how big can x in any given series be, how small can it be, and such that the values in the middle will converge. So for example, you can see that this is all just some r in a geometric series. And we know as long as the absolute value of that r is less than 1, the series will converge. So what interval is this? Well, we can set x minus b less than 1 and x minus b greater than negative 1, right? As long as this value is between negative 1 and 1, this will be satisfied. So we want it to be greater than negative 1 but smaller than 1. And if you solve both of these, you'll see that x has to be less than 1 plus b, and here x has to be greater than b minus 1. So as long as b minus 1 is less than x, which is less than 1 plus b, our series will converge. In interval notation, we could write that as b minus 1 to b plus 1. So if x is anything smaller than this or bigger than this, the series will diverge. But if it's anywhere in between those values, it will converge. In this case, we know that if we were to plug in exactly b plus 1 in for x, we would get a times 1 to the n power, which we know diverges because 1 is not less than 1. 1 is equal to 1. So in this case, we're going to use soft brackets, open brackets, because we do not want to include b minus 1 and b plus 1. But in some cases, we're going to include those brackets. Let's look at the next question. Determining the convergence of this series. So let's see. Like I said, we're going to be using the ratio test. That was just a unique geometric series case, but let's use the ratio test. Let's say the limit as n approaches infinity. First, let's outline what is a sub n plus 1. That just means everywhere you see an x or an n, you want to put an n plus 1. So it'll look like this. And a sub n is obviously what we started with. So when we take the limit of the absolute value of the ratio between them, x to the n plus 1 over n plus 1 squared, all over x to the n over n squared. When you divide fractions, you can just keep change flip. So let's do keep our first one, keep our first fraction, and instead flip the other fraction and multiply it instead. So multiply by the reciprocal of the original. And remember, from the ratio test, we want this limit to be less than 1. So let's see what x values will make that true. Well, you can see that at infinity, this right here is, n squared plus 2n plus 1. But at infinity, if we're have an n squared on top and this quantity on the bottom, they're really just going to cancel out because these terms right here don't really affect our limit at infinity, so we can ignore them. And then you can see we have n squared over n squared. So those two quantities kind of cancel each other out at infinity. So we're left with the limit as n approaches infinity of x to the n plus 1 over x to the n. And there's two ways to look at this. We remember that x to the n plus 1 is the same thing as x to the n times x to the 1. Because remember, if you have the same base here, you can just add their exponents. The other way so we could rewrite this as the limit as n approaches infinity of x times x to the n over x to the n. And obviously that x to the n is going to cancel that one. We want that to be less than 1. The other way to think about this would be, remember that if you're dividing two, and they had two bases, you can just subtract their exponents. So what is x to the n plus 1 minus n? You just get x to the 1. So either way, you're going to end up with just an x to the 1 in there, right? So we want that to be less than 1. Well, what is the limit as n approaches infinity of x? There's no n's, so that's just going to be the absolute value of x. We can just drop the limit. So this is our answer. We want the absolute value of x to be less than 1. So x can be anywhere between -1 and 1. But my question is, could it be exactly 1 or exactly -1? How are we going to check that? Well, let's look at our series here, the one we started with, and just plug in 1 and -1 and see what happens. So we call this checking the endpoints. Let's check the first endpoint, -1. Let's just look at this series by itself. -1 to the n over n squared. So this is an alternating series. Actually, let me write this one down too. N equals 1 to infinity. If we were to just plug in 1, we get 1 to the n, but 1 to the n is just 1 over n squared. Now just ask yourself, do these series converge? Well, this is a p series, right? And p is greater than, p is equal to 2, which is greater than 1, so this series converges. We looked at that in the series video, the second video in this chapter. So this series converges. What that means is that we can include 1. Also, how about this one? This is an alternating series. We also looked at alternating series in a video. We say that these alternating series converge if two conditions are met. One, it has to be decreasing. And 2, the limit as n approaches infinity of a sub n must be 0. So let's see, this is obviously decreasing because the top's bounded between -1 and 1, and the bottom is growing without bound. For example, if you plug in 1, you're just, ignore the top. If you plug in 1, you're going to get 1 over 1. But if you plug in 5, you're going to get 1 over 25. If you plug in 10, you're going to get 1 over 100. So the terms are decreasing. You could also plug in the function 1 over x squared into your calculator, and you'll see that it decreases over the interval from 0 to infinity. Okay, so how about when you plug in infinity? Well, once again, the top is bounded, the bottom's going without bound. So yes, it's getting smaller, and the limit is equal to infinity. So we could say that this converges by the alternating series test. This converges by the p-series test. But remember, with the alternating series, we have to determine if it's absolutely convergent or conditionally convergent. But actually for this section, we don't have to. As long as it converges either conditionally or absolutely, we can include it in this bracket. Because whether it converges conditionally or absolutely, it converges, right? So we'll fix this bracket to instead say -1 to 1. This is our new interval. of convergence. So, to recap, if you plug in into this series right here, any number between -1 and 1, including -1 and 1, the series will converge. So the reason why this is useful is because if someone said to evaluate this series at 2, and maybe they want you to do the 2, and they want you to do it again, but change the 2 to a 3, and they want you to do it for several different values on top, you could just put an x there, see what x can be using the ratio test and with the power series, and then you can easily see that if you plug in any number that is outside this interval, it will diverge. So remember back to what we were saying, is that over here, in the last two cases we looked at, we were looking at number 3. There was an interval of convergence where the series will diverge if it's outside of that. So maybe one of these first two will pop up, but that's what we were looking at with the number 3, about the interval of convergence. So let's look at the next one. We have x minus 4 to the n power over the quantity n times 5 to the n. So remember, start out with our ratio test, and we will plug everywhere we see an n, we're going to do an n plus 1. And then instead of dividing by a sub n, we're just going to multiply by the reciprocal of a sub n, which is n times 5 to the n over x minus 4 to the n power. And we want this limit to be less than 1. So let's see what we can do. Well, using the same strategies we looked at in the last one, we could rewrite this as x minus 4 times x minus 4 to the n. Right, that's the same thing as this. And we could rewrite this as n plus 1 times 5 times 5 to the n, right? Same thing here with this. And then we'll keep the right side. And let's see what we can cancel. We have an x minus 4 to the n power on top, x minus 4 to the n power on bottom, 5 to the n power on top, 5 to the n power on the bottom. And what is the limit as n approaches infinity? Well, just like we looked at in the last time, this 1 right here is really doing nothing. And n over n cancel. So the limit, and that's only at infinity, like n over n plus 1. If you were to plug in, 1,000 for n, you'd get 1,000 over 1,001. And that's already basically just 1, right? 0.999. So now imagine it was 10,000, 100,000, infinity. N over n plus 1 is really, we could just consider it to be 1 at infinity. So what is, this is going to be the limit as n approaches infinity of x minus 4 over 5. We want that to be less than 1. So let's look at, and remember, there's nowhere to plug in an n anymore. Oh no, we did the n. That's what we were left with. That's what the limit is. Okay, so let's solve this inequality. This is the same thing as x, absolute value of x minus 4 has to be less than 5. So once again, we could say that x minus 4 has to be less than 5, and that x minus 4 has to be greater than negative 5. This tells us that x has to be less than 9, but that x has to be greater than negative 1. So right now our interval of convergence is negative 1 to 9. You could also say that your radius of convergence, that's a term that comes up a lot, the radius is 4. Because if you were to put this on a number line, right, say we had a number line, and this is infinity, negative infinity, we want to say what can x be and not be. So if this is 0, and here's a negative 1, and here's 1, 2, all the way to 9, we can say that x can be anywhere in this interval from 9 to negative 1. So at our center here at 1, or I should say, actually, our center here at 4, our center would be over here at 4. The radius can go either direction. So the radius is not 4, the radius is 5. It can go either direction, a total of 5. No, I messed up. The center's at 5. The radius is 4. Center's at 5. It can go 4 in either direction. Right? No. Okay, I had it right the first time. The radius is 5, and it's centered at 4. We know that it's centered at 4 because of this right here. Right, this is C. We know it's centered here at 4. So the radius, and we can see that the radius is 5. So we'll say it's centered here at 4. It can go either direction, 5, right? It can go 5 to -1 and 5 to 9. So we'd say that this is our interval of convergence, I, O, C, and the radius is equal to 5 because we can go in either direction. Okay, got that cleared up. Now, remember, we want to check the endpoints. That's common. So let's look at first the series where you plug in -1, and we'd be left with this, -5 to the n power over n times 5 to the n. And then secondly, we want to look at the series where you plug in 9, and we'd be left with 5 to the n over n times 5 to the n. Well, I'm sorry, not 5. Yeah, 5 to the n. So we can see the 5 to the n's cancel, and we're left with just 1 over n. And we know that the series from n equals 1 to infinity of 1 over n, we looked at, you could prove it with the p series. This is a power series. P is equal to 1, which is not, it's not greater than 1. It's not greater than 1, so it is said to diverge. This is also what we looked at, the divergent harmonic series. So we know that this one diverges. So basically, we'll keep this bracket open. Okay, and then let's look at this series. -5 to the n power. What are a few terms of that? -5, 25, -125. Can we rewrite this as -1 to the n power times 5 to the n power? See, now when you plug in 1, you're going to get a -1 times a 5. If you plug in 2, you're going to get a +1 times a 25. So you'll see that matches up the same. The reason I want to do that is because now we can write this series as -1 to the n times 5 to the n over n times 5 to the n, and we can cancel out those 5 to the n's again. So this series is an alternating series, and this is a conditionally convergent alternating series because it meets the requirements of the alternating series theorem or the alternating series test. Yes, it's decreasing, and yes, its limit is 0 as n approaches infinity. But if we were to remove that alternating term, like this one right here, it would be divergent. So we said this is conditionally convergent, but remember, we don't care about the conditionally part. We just know that it's convergent. So we do want to include, or we don't want to include 9. Right, earlier when I said this open bracket, we were testing 9 with that second interval. So we want to keep that one open, but we know that we can include -1 because it is conditionally convergent, but forget about the conditionally part, it is just convergent at -1. So we can see on this number line, it can be -1, can't be 9. So we'll say that this interval of convergence is including -1, but not 9. So as long as x is -1 or anything less, or between 9 and less than 9, this series right here will converge. Okay, so let's look at the next problem. So for this problem, once again, we're going to do a ratio test. Limit as n approaches infinity. We're doing x plus 1 times x plus 1 to the n. Let's skip that step. Then you have an n plus 1, n plus 2, right? N plus 1 plus 1. And then we're going to do n plus 1, x plus 1 to the n. So this right here was, this right here was a sub n. I just skipped the step of writing this as n plus 1 and just took that out of the exponent. So we can see that x plus 1 to the n cancels with the 1 on bottom. And remember, at infinity, this is growing just as n squared. And this is growing just as n squared. So those cancel each other too. We're just left with the limit as n approaches infinity of x plus 1. We want that to be less than 1 in order for it to converge. So x plus 1 has to be less than 1, meaning that x plus 1 has to be less than 1, and x plus 1 has to be greater than negative 1. So x has to be less than 0, but x has to be greater than negative 2. So we could say that this is 0 to negative 2. And I have that backwards. It should be negative 2 to 0, right? Right over here. And now let's check those endpoints. So let's plug in negative 2, and we get this. Negative 2 plus 1 is negative 1 to the n power, divided by n times n plus 1. So let's check that series. That'll be for our first endpoint. For our second endpoint, we will look at the series from n equals 1 to infinity of negative 2 plus 1, which is positive 1 to the n power, okay. Remember, 1 to the n is the same as just 1. So let's look at these series. Do they converge or do they diverge? So for this series, again, it's an alternating series, so we'll just use that AST, alternating series test. 1, is it decreasing? Yes, the bottom's going without bound and the top's bounded. And 2, is the limit as n approaches infinity equal to 0? Yes, because the top's bounded and the bottom's going without bound. So it converges. Whether conditionally or absolutely, we don't care, as long as it converges. This one, I can see that this is similar to this convergent P series, right? Except in the bottom we have that n squared plus n. So this extra n is causing a problem, right? But it's very similar to this convergent series. It's very similar to that one. So remember, if it looks very similar to a series you know to converge or diverge, we can do a comparison test. So you can look back to that video if you remember. You take the limit as n approaches infinity of the absolute value of your convergent or divergent series, b sub n, over the series that you're concerned about. And as you've seen so many times in this video, this bottom one is really just going to grow like n squared. That n is not doing anything at infinity. And 1 over n squared over 1 over n squared cancel, and you just get 1. 1 is a finite non-zero number, and the limit comparison test says that as long as the limit is a finite non-zero number, it will match the convergence of b sub n. So that doesn't mean it's going to converge or diverge. It means it's going to match whatever you compared it to. Since 1 over n squared is a p series, where p is equal to 2, which is greater than 1, it converges. So we'll say that this converges as well. So since it converges both at negative 2 and 0, we'll say that this is our updated interval of convergence. The radius is 1 in this case, because it's centered at 1, or it's actually centered at negative 1, and it can go 1 in either direction. Okay, how about the next one? So factorials. Remember, the ratio test is already good when we have something, or the n in the exponent, and it's especially good with factorials as well, because we can do a lot of cancellation. So the limit as n approaches infinity, the absolute value of n plus 1 factorial. Remember, we want that plus 1 to be inside the factorial. And then n times x to the n over 2 times n plus 1 factorial. So we don't want it to be 2n plus 1. We want it to be 2 times the quantity n plus 1. And then we're going to flip what we originally had. See what we can cancel. So those cancel just like usual. How about what's left? Well, n plus 1 factorial is the same thing as n plus 1 times n factorial. And 2n plus 2, right, because that's what that bottom one turns into, 2n plus 2 factorial is the same thing as 2n plus 2 times 2n plus 1 times 2n factorial. So if we substitute those in, we're left with just an n plus 1 on top, right? Because the n factorial here on top cancels with the 1 on bottom. That one will cancel with the 1 on bottom. And this 2n factorial on top will cancel with the 2n factorial on the bottom. So we're left with just this on the bottom and just this on the top. N plus 1 over 2n plus 2, 2n plus 1. And over here, this should not be in n, that should be in x, right? There's our x. We want that to be less than 1. So what is this limit? Well, remember what we like to do at infinity. This 1 really does nothing. This 1 and this 2 don't really do anything. So this is kind of like the limit as n approaches infinity of n over 4n squared times x. So one of those n's can cancel with 1 on bottom. And when you plug in infinity, you get infinity on the bottom. So this limit, regardless of what x is equal to 0. Because the bottom's growing without bound and the top is bounded at 1. So the limit's 0 no matter what x is. 0 is always less than 1. So no matter what x is, the series converges, right? We could say that x can be anywhere from negative infinity to infinity. The limit's always going to be 0 because of this n on the bottom. So this is our interval of convergence. Remember at the beginning of the video when I said this is going to be one of 3 possibilities. In the last 4 examples, we looked at this case. Now this is popping up. It will converge for all real numbers. Let's see if we can run into number 1 in the next problem. So in this problem right here, I think this is the last one. Once again, we're going to do a ratio test. I'm going to take the ratio of x minus 5 times x minus 5 to the n power times n plus 1 factorial over 2 times 2 to the n power. So that's our a sub n plus 1. We're multiplying that with the reciprocal of a sub n. Let's see, the n, or the x minus 5 to the n cancels with the x minus 5 to the n on the bottom. 2 to the n on top, 2 to the n on the bottom. And remember, we could rewrite that n plus 1 factorial as n plus 1 times n factorial, and now cancel it with the 1 on bottom. Okay, so that leaves us just an n plus 1 on top. And let's see, this turns into now the limit as n approaches infinity of x minus 5. We have this n plus 1. And we do have a 2 on the bottom. What happens when you plug in infinity? You just get infinity, right? Because the top's growing without bound now. Infinity is always greater than 1, so by the ratio test, no matter what x is, it will diverge. The series will diverge, that is. This series right here, this series will diverge since we took the ratio test, and it was always infinity, and infinity is greater than 1. But is it always infinity? We don't really know a lot about infinity, but we do know that 0 times infinity is 0. We don't know, infinity times infinity. We don't know infinity divided by infinity. These are all indeterminate forms, but we do know that 0 times infinity is 0. So, what happens if x is 5? If x is 5, when x equals 5, the limit, as n approaches infinity, of that stuff is equal to 0, because the inside 0, the limit as n approaches infinity, of 0 is 0. So if x is 5, the limit is 0, which is less than 1. So x equaling 5 does correspond to a convergent series. But we kind of knew that already from the start, right? If we were to plug in a 5 there for x, you would just have a 0 on top, and therefore 0. And this doesn't really, the series of 0 doesn't really mean anything, because it's just, but it technically converges. So this is the case of case equals 1. there's one particular x value where the series is convergent, right up here. It will converge only for, not x equaling 0, I should write this, for one value of x, which makes the series 0, so only for the series being 0. So not x equals 0, but x equaling really just that center C. So that is the power series using the ratio test to determine how big or small x can be to see if the remaining series is convergent.